Welcome, aviation enthusiasts and curious minds, to a journey through the skies like never before. We're about to embark on a thrilling exploration of the most unusual and innovative planes that defy the conventional norms of aviation. The Miles aircraft concern conceived the M39 Libellula during the early 1940s, amid the turmoil of World War II. Initially, the concept aimed to simplify landing aircraft on carrier decks, addressing visibility challenges caused by forward-mounted engines and large wing mainplanes. A novel tandem wing arrangement was pursued to mitigate risks, resulting in a series of concepts explored by Miles during the war. The overarching term for these Miles designs was Libellula, named after the taxonomic family of the dragonfly. The groundwork for this project began with the M35, essentially a technology demonstrator for a single-seat naval fighter. Miles pursued this endeavour independently, using the tandem wing setup to reconfigure the centre of gravity found in conventionally configured military aircraft. In a brief span of 6 weeks, Miles engineers introduced the M35. This aircraft was equipped with a single de Havilland Gypsy Major air-cooled inline engine, boasting 130 horsepower. During testing, the engine exhibited temperamental behaviour and longitudinal control was problematic. Nevertheless, this design provided valuable insights into the unconventional arrangement, contributing to future developments in the field. Building on this knowledge, a new design emerged, scaled at 5/8 and designated as M39B. This single-seat demonstrator featured a pair of de Havilland Gypsy Major IC air-cooled inline engines, each with 130 horsepower, showcased in outboard nacelles beneath the rear wing mainplanes. The frontal mainplane was now positioned low against the sides of the cockpit, and the fuselage boasted a finely contoured shape from nose to tail. The undercarriage transitioned to a traditional tricycle configuration. Given the larger scope of the M39B project, its dimensions were appropriately increased. The wingspans now measured 25 feet at the front set and 37.5 feet at the rear. The overall length extended to 22.3 feet, and the maximum weight rose to 3,200 pounds. As constructed and tested, the M39B achieved speeds of up to 166 miles per hour thanks to its twin-engine setup and tandem wing approach. The maiden flight for the M39B occurred on July 22, 1943. A dorsal fin was later fitted at the fuselage aft for additional control to complete the M39B's iconic three-finned appearance. Up until September of 1943, all of the work on the two aircraft, M35 and M39B, was as a private venture. From then on, the British Air Ministry decided to offer a formal development contract to Miles. Shortly after, Miles sought interest from the United States Army Air Forces, aware of their consideration of the domestic Curtiss XP-55 Ascender, which shared a tandem wing pusher engine configuration and was intended as a fighter. The USAF's response revealed a general lack of interest in the Miles product, as the XP-55 itself faced issues, particularly with stalls and recovery. The American program only progressed to flight testing, producing 3 aircraft in total. The M39B underwent evaluation at the Royal Aircraft Establishment, encountering problems from the outset. A new undercarriage had to be installed, and several accidents necessitated constant repairs, keeping the aircraft grounded for extended periods. Despite its unconventional arrangement, overall handling characteristics were considered normal. While landing and takeoff required adjustments to the standard routine, these were deemed forgivable, and stalling and recovery performed as anticipated. In 1941, the RAF issued a new specification for a medium-class, medium to high-altitude, high-performance bomber. Miles responded with its M39 project, a modified version of the M39B featuring a pressurized cockpit for a crew of 3. The proposed power for the M39 project included either 2 Rolls-Royce Merlin 61 series inline engines or 3 Powerjet's W2500 gas-powered turbine engines. This design featured a significant wingspan increase, measuring 37.5 feet at the frontal wing and 55.8 feet at the rear pairing. The overall length expanded to 35.9 feet, and the maximum weight surged to 26,750 pounds. The envisioned cruising speed was 360 miles per hour, and armament was planned to include two 20mm cannons in the wing roots, one gun per root, along with an internal bomb bay in the fuselage, capable of carrying up to 6,000 pounds of bombs. Ultimately, the de Havilland DH-99 Vampire fulfilled the specified requirements. The Hawker P-1005 also competed for a period. Although a prototype M39 high-speed bomber was ordered under a November 1943 contract, it was never constructed. The RAF's bomber needs were met elsewhere, leading to the termination of the M39 project, along with the data-collecting M39B aircraft. While surviving the war, the M39B lasted only until 1948, when it was scrapped. Despite its shortcomings, the Miles Libellula left an indelible mark on aviation history. Its bold, unconventional design inspired future aircraft engineers to think outside the box and take risks. The Libellula remains a testament to the power of human ingenuity and the boundless potential of innovation. The Miles M39B Libellula serves as a fascinating case study of a daring, experimental aircraft that ultimately fell short of expectations. Its unique design, ambitious goals, and ultimate cancellation offer valuable lessons for future aviation endeavours.
During the course of World War II, German aircraft designers embraced many unusual concepts. Some worked, but not all. The Blumenvoss P-163, a product of the mind of Richard Vogt, a German aircraft designer who conceived of many weird and wonderful designs during World War II. At a time when the shortage of aluminum was starting to affect aircraft production, the P-163 concept offered a way of partially utilizing steel as an alternative, at least in a limited way. Of course, there would be a weight penalty. However, the additional strength of steel might allow the wings to support a crew gondola and each wingtip, thereby allowing much more free space in the main fuselage for engines, weapons, and fuel. Each of the gondolas would have weighed about 1 ton. Vogt predicted that they would actually improve flight performance by reducing both bending in the wings and turbulence from their outer edges. Project 163 was envisioned as a high-speed bomber, fulfilling some of the multiple roles performed by the famous Junkers Ju-88. The Junkers plane was clearly in the fast bomber class. It had a crew of 3 or 4, grouped together to improve morale and enable better communication. However, the aircraft was lightly armed and relied mainly on speed for survival against enemy fighters. In contrast, the design of Blumenvoss's new proposal necessitated having 2 separate crew seating positions, separated by at least 60 feet. The 163 was manned by a crew of 4, with 2 men in each gondola. There would be a single pilot who would have a spectacular view, not disrupted by turning propellers. More significantly, the pilot sat back-to-back with his navigator and part-time gunner, who was in an excellent position to cover the rear and left flank of the aircraft. To balance the architecture, Project 163's other gondola had 2 gunners, one facing aft, the other forward. At least in theory, this high-speed bomber would have been very well protected. Not surprisingly, there were serious concerns about the actual control of such a revolutionary layout. How would a pilot react to being at the very tip of an aircraft rather than the center? To test the impact of this position on the pilot, an early asymmetric Vogt design was modified. An additional gondola was added to the BV-141's port wing and tested. Another major advantage of the wingtip cockpit was that it would leave the 163's main fuselage less cluttered, leaving space for a power plant that consisted of two engines coupled together, driving counter-rotating propellers in a center-line thrust. At about the same time that Project 163 was being developed, the center-line thrust approach was also being explored in the south of Germany by the Dornier Company. Their DO-335 Arrow heavy fighter bomber design was also based on the principle of center-line thrust. One engine set in the traditional nose position, and another placed in the center of the fuselage, driving a propeller at the very back of the aircraft. In the United States, another company, Douglas Aircraft, were also engrossed in another center-line thrust project, which was just as revolutionary. The XB-42, or Mixmaster, was designed as a fast, long-range bomber. It employed two engines mounted near the middle of the airframe, driving separate propellers grouped together at the rear. The XB-42's layout, like that of the DO-335, resulted in extremely clean flying surfaces that made for increased speed and maneuverability. Both aircraft were finally made, and with testing so advanced, they probably would have gone into production if the war had continued. Meanwhile, back in Germany, the war was not going well, and the benefits of all new aircraft projects were being seriously reappraised. Although it was reasonable to assume that Blum and Voss had a design that would be the equal of the Junkers Ju-88 in speed and range, and it would also have offered considerably more defensive gunnery, there was still caution about the practicality of the crew positions. How would pilots feel about such an unusual design? The acid test would be the adapted 141 asymmetric plane. The standard BV-141 actually worked quite well. The addition of yet another gondola at the very tip of one wing made the aircraft even more bizarre looking, but it served its purpose and apparently proved that the wingtip cockpit arrangement was workable. However, workable just wasn't enough. Project 163 was cancelled before a prototype was built. There would be no armadas of this unusual-looking aircraft flying over enemy targets, and the addition of another gondola at the very tip of one wing did not turn it into a swan. But it served its purpose and apparently proved the wingtip cockpit arrangement was acceptable. Another factor behind the decision to cancel the 163 was its performance. It simply did not offer any major improvement on what was already proven and available. But performance was not Richard Vogt's primary objective in designing the 163. His goal was to find a way of substituting steel for aluminum, which at the time was in short supply. But as the war progressed, not only aluminum, but all materials in Germany were in short supply. But Richard Vogt's revolutionary concept would later be vindicated by the United States Air Force. In 1949, the Northrop F-89 Scorpion was finally selected by Air Defense Command as its mainstay all-weather interceptor. It was to be armed with cannons, but the A, B, and C models displayed structural problems in the wings, and there were some losses. In 1954, the D model entered service. This had a much strengthened wing and a huge pod mounted on both wing tips. Each pod contained 52 Mighty Mouse rockets. The F-89D became the main production version of the Scorpion, and perhaps supported Vogt's theory on wing bending and turbulence. The post-war B-17 clearly demonstrated the benefits of Vogt's wingtip theory.
We had a B-17 there that had a crew position on a right wingtip. The reason they did that was to develop central gun control So they had this on the V-29. However, it wasn't on a wingtip. But that was what the airplane was built for. However, the war was over and everybody forgot about that, except the Aeromed people thought, oh, what a wonderful thing to find out what it is like to roll an airplane if you're not on the roll axis. Everybody said it didn't make any difference, but they insisted on doing it, and they built a cockpit in that position out there using the formation stick, which was worked through the autopilot, and you could fly the airplane from this position out on the wingtip. So I got to fly it. The one thing you did learn was, you know, when you're in turbulent air, you keep seeing the wings flap up and down. That's not exactly what's happening. The tips are more or less steady. It's the fuselage that's moving up and down. And you could sit out there on that wingtip and jiggle the formation stick longitudinally and make the people in the airplane sick, and you were hardly moving. But you didn't do it too much because they'd get mad at you and get even with you later.
In recognition of his genius, Richard Vogt was invited immediately after the war to work in America. He contributed to many designs, including the ambitious Tiptoe project and its many variants.
In the post-World War II era, the concept of military aircraft capable of vertical takeoff and landing, VTOL, captured the imagination of designers and military strategists globally. The increasing performance of land-based jet aircraft necessitated longer runways, which in turn presented vulnerabilities. A single conventional bomb on a runway could incapacitate an airbase and its aircraft. Naval aviation faced similar challenges, as aircraft carriers were susceptible to attacks. Despite the number of combat aircraft a carrier could operate, any damage to the vessel rendered its air power ineffective. The idea of VTOL-capable aircraft emerged as a potential solution to these issues. Such aircraft could be launched and recovered from small, temporary forward air bases or even from vessels considerably smaller than traditional aircraft carriers. Recognizing the strategic importance of VTOL capabilities, the USAF and US Navy jointly sponsored Project Hummingbird in 1947. This project aimed to explore and study the practical application of VTOL technology, laying the groundwork for innovative designs like the Convair XFY-1 Pogo that would follow. This project was able to use data captured from Nazi Germany at the end of World War II, and, in particular, design work on a projected German VTOL aircraft, the Focke-Wulf Triebflügeljäger. The Triebflügeljäger was a radical design concept created in 1944 in response to the increased Allied bombing of German industrial targets. Its design never went further than the creation of wind tunnel models, but the concept of a tail-sitter VTOL aircraft captured the interest of the US Navy. They were interested in a fighter that could be launched from any warship and even from transport ships or tankers. The prospect of equipping each US Navy ship with its own point defense interceptor led to a significant re-evaluation of the necessity for vulnerable aircraft carriers. Building on the findings of Project Hummingbird in 1948, the US Navy initiated a more detailed study and, in 1949, sought the expertise of the National Advisory Committee for Aeronautics to assess the feasibility of developing a tail-sitter VTOL interceptor. This concept, resembling the Triebflügeljäger in some aspects, employed a conventional fuselage with an engine driving contra-rotating propellers in the nose. A successful model demonstrated the ability to take off and land vertically, seamlessly transitioning to conventional forward flight. In May 1951, the US Navy awarded contracts to both Convair and Lockheed for the production of 2 prototypes, each of a VTOL tail-sitter fighter. Both the Convair and Lockheed aircraft were slated to be equipped with the powerful Allison T-40 engine, a development based on a pair of T-38 Allison turboprop engines arranged side by side, delivering power to a shared reduction gearbox. This marked a significant step forward in the pursuit of effective VTOL capabilities for naval interceptors. The power of the engine was estimated to be over 5,000 kilowatts. In comparison, the Pratt & Whitney radial engine fitted to the Vought F-4U-4 Corsair, then in service with the US Navy, provided around 1,700 kilowatts. The pilot's seat was able to rotate through 45 degrees to allow it to be used comfortably in both vertical and horizontal flight. No armament was ever fitted to the XFY-1, but this was expected to take the form of either 4 20mm cannon fitted in the wing's outboard of the massive propellers, or a pack containing 48 folding fin unguided aerial rockets. The first XFY-1 prototype reached completion in early 1954 and underwent testing in a fixed vertical stand at Lindbergh Field in San Diego. The performance in this setting was satisfactory, prompting the decision to proceed with the next phase of development, involving tethered and untethered flight testing. The second prototype was transported to NAS Moffett Field near Sunnyvale, California, where a specially designed tethered test rig was set up in the colossal Hangar No. 1. This historic hangar, originally constructed in the 1930s, once housed the US Navy airship USS Macron. The rig featured a motorized reel attached by cable to the XFY-1 propeller hub, providing a means for emergency reeling to swiftly return the aircraft to an upright position. The challenging task of determining whether the XFY-1 could actually fly fell to Lieutenant Colonel James F. Skeets Coleman, a US Marine Corps Reserve pilot and engineering test pilot for Convair. Tethered flights were conducted with assistance from Convair flight test engineer Bob McGreary, who controlled the tether mechanism, ready to pull the XFY-1 upright in case Coleman lost control. Coleman faced the daunting responsibility of testing an aircraft that was both radically different and potentially hazardous, making his role as a test pilot exceptionally challenging. In November 1954, Lieutenant Colonel James F. Skeets Coleman achieved a significant milestone by executing the first transition to horizontal flight in the XFY-1. Remaining in conventional forward flight for over 20 minutes, he safely returned the aircraft for landing. The XFY-1, powered by significant thrust in a compact and streamlined airframe, proved to be remarkably fast. Even with throttles at their minimum setting, the aircraft cruised at speeds exceeding 300 miles per hour. During level flight, it often surpassed the conventional chase aircraft assigned to monitor its progress. The absence of speed brakes or spoilers made landing at these high speeds particularly challenging. To address this, Coleman developed a unique landing technique. Approaching the landing field at around 300 miles per hour, he would pull the stick all the way back when close to the landing point, causing the XFY-1 to enter a vertical climb. As the speed decreased, he carefully added power until the aircraft reached a hover at an altitude of around 1,000 feet. Then, while looking over his shoulder at the ground, he gently reduced power during the descent. The XFY-1's lack of stability in the hover demanded constant control corrections during descent, especially as it encountered turbulence from its own reflected prop wash near the ground. One of the most demanding aspects of landing involved judging the aircraft's rate of descent within safe limits, a task requiring the pilot's attention to the ground over his shoulder and continuous control input to maintain stability. The unique characteristics of the XFY-1 demanded exceptional skill and precision from its pilot during the landing phase. As an aid, Convair mounted a small radar altimeter pod on the left wingtip. This was connected to 3 lights in the cockpit. Green meant that the aircraft was in a stable hover, amber meant that it was descending within safe limits, and red meant that the rate of descent was too fast. Even with this device fitted, the XFY-1 was a fiendishly difficult aircraft to land. Coleman was clearly an exceptional pilot, and when another US Navy pilot was allowed to fly the XFY-1 for the first time in May 1955, he was lucky to survive the experience. The XFY-1 never took to the skies again, and the project officially concluded in August 1956. Lockheed's XF-V1 tailsitter too was abandoned without achieving vertical takeoff or landing. From a strictly technical standpoint, the XFY-1 demonstrated success. It executed numerous flights, showcasing its ability to fly conventionally and to perform vertical takeoffs and landings. In this limited sense, it marked the first successful military VTOL aircraft. However, as a potential operational aircraft, the XFY-1 faced insurmountable challenges. Landing safely was an exceedingly difficult task. Lacking automated flight stabilization in the hover, it demanded constant corrections from the pilot, who also had to closely and continuously monitor descent rate, position, and attitude. The second critical issue leading to the project's cancellation was performance. By the mid-1950s, jet interceptors capable of exceeding Mach 1 were being produced. In just a few years, operational aircraft would achieve Mach 2 capabilities. Despite the formidable power of its turboprop engine, the XFY-1 could never reach even Mach 1. This limitation placed it at a distinct and insurmountable disadvantage as a combat aircraft, making its operational viability untenable in the face of evolving technological standards.
Lithe, graceful, and deadly, the pterodactyl was one of the first known reptiles that evolved powered flight. Its wing movements held within them a beautiful science that would live on long after the end of the prehistoric world. But out of the remnants of that distant past, one 20th century inventor created a method of flight that would change aviation's future. In the designs of Geoffrey Hill, the swept-wing tailless plane would not fly as a machine, but in the same style as a living animal. And the pterodactyl would find life again in a new man-made body, but would soar above the earth just as it always had. The dust had barely settled from the Second World War when Allied forces started to exploit the treasure trove of aerodynamic data collected by the defeated Luftwaffe and its various manufacturers. Britain too followed suit in sharing the spoils of war. Many German aviation concepts were seriously considered and in fact ultimately employed. At the same time, the British government could sense the onslaught of the Cold War and wanted to be ready in case tensions between the US and the Soviet Union suddenly turned hot. The nation was deeply in debt, but homeland security was still given top priority, which is why the British Ministry of Supply issued an order for a new bomber. History would later call this order the V-bomber specification. The government was looking for a long-range aircraft that would employ the jet power technology discovered but not used to its full capacity during the war. Coupled with the aerodynamic marvels developed by the Germans, Britain was determined not to be caught off guard in the event of a nuclear conflict. The Americans had already shown the might of their atom bomb at the end of the war, while the Soviets got a jump start on their own program by exploiting German nuclear resources.
The best recent study by David Holloway on Stalin and the bomb has come to the conclusion that the Soviets were really disappointed at the sort of technological level of the German nuclear program, and that the chief gain for them was not the sort of technological know-how of the German scientists, but the uranium, the processed uranium that they managed to get their hands on, which in Holloway's estimation probably saved the Soviet nuclear bomb project about a year.
Britain was developing its own bomb program and felt the first things it needed were bomber aircraft advanced enough to carry the load. 4 submissions from 4 different British manufacturers were ordered to go into production. 3 of the planes employed technology that was borrowed from newly accessible German research. Because of them, history would look back on this era as the golden age of British bombers, where grace, beauty, power and efficiency were all ingredients used to produce the majestic aircraft of Britain's V-bomber force: the Vickers Valiant, the Avro Vulcan, and the Handley Page Victor. Of these 3 bombers, the Valiant had the least sophisticated design, but was the first to see flight time, with a prototype taking off in 1951. This was a conservative but cleanly built aircraft and could accommodate a 10,000-pound bomb. In fact, the very first British atomic weapon, a live Blue Danube, was dropped during a 1956 test in Australia using the Valiant B-1. Despite being the least advanced of the V-bombers, the Valiant was the first to fulfill the purpose for which it was built. In contrast, the Avro-Vulcan was a sleek subsonic bomber and sported a unique delta wing configuration that set it apart. Its wingtip rudders gave it control, even while carrying 21,000 pounds worth of bombs. Of all the V-bombers, the Victor was regarded as the most futuristic and avant-garde in both looks and performance. Because it was specifically designed to quickly invade Soviet airspace, it could fly higher and faster than any of its contemporaries. Despite the defense capabilities these three planes gave Britain, it was interesting that none of them was 100% British. Each had its origins in the seized German research. There was, however, the fourth V-bomber submission that the government rejected as being too ambitious. It was the Short Brothers PD-1, a medium-range bomber design that had very little to do with seized German technology and more with a single flying wing. To help create this advanced aircraft, the Shorts team recruited an engineer who was famed for his work in tailless plane design, Professor Geoffrey T.R. Hill. Despite Hill's involvement, the PD-1 never made it past the design stage. But it did later take on other forms and names before claiming its place in the books as the Shorts Sherpa, a highly developed unit that sported a unique swept-back wing design that Hill specifically created for this project. The fact that both the Sherpa and the PD-1 had their roots in wholly British research made it ironic that the Ministry of Supply declined to produce the PD-1. This research began a full generation before the other V-bombers were even drawn up. In fact, it was spearheaded by Hill in the 1920s as a series of tailless planes called Pterodactyls, aircraft designed for superior flight safety and control. But in spite of Hill's achievements as a pioneer of swept-wing, tailless flight, and in spite of his role in the development of the PD-1 and the Sherpa, he was ultimately disregarded by the aviation community towards the end of his career in the 1950s.
At that time, he might well have been a forgotten man, inasmuch as none of his designs had been taken up. But I think that's only part of the story.
As far as I know, in the later part of his life, he was desperately disappointed that all of the work and the really brilliant and inventive work that he had done had not really apparently got real tangible results, although there were aeroplanes coming out of Short Brothers that were important.
Hill believed that a swept-wing, tailless aircraft represented a more natural method of flight. But he wasn't the one who started the movement. It all began in the early 1900s with a pilot and designer named John William Dunn, whose work greatly influenced Hill. Dunn's goal was to develop a flying machine that required no steering. He designed aircraft for Britain that always bore the distinctive V shape of an arrowhead, later to be known as swept wings. The original Dunn biplane was such an achievement that almost a full century later, a Canadian mechanical engineer named Barry McKerracher built a full-sized replica of a later version called the Burgess Dunn. Now permanently on display at the Royal Canadian Air Force Museum in Trenton, the plane is the spitting image of the 1914 Burgess Dunn, from the pilot's seat to the copper gas tanks to the airframe. But the plane's swept wings were its most revolutionary feature.
This particular airplane would not fall or stall. As it lowered its airspeed, it actually dipped the nose down, picked up speed, and then came back up again. It didn't fall off to either wing, which is some things that happen to straight normal biplanes or wings.
The idea would change conventional aviation, but Dunn had a hard time proving it. Almost a decade and 4 limited prototypes later, the military had had enough of Dunn's seemingly quirky planes. Spurred on by financial support from his friends, he built and successfully flew the Dunn D-5 tailless biplane. Dunn soon built more prototypes, including the smooth and stable D-8, which is what caught the eye of an American boat and aircraft builder named Starling Burgess. After Burgess bought the US manufacturing rights, the Burgess-Dunn biplane began its development. Its full wingspan was 47 feet, but the fuselage itself was only 26 feet long. There were 2 seats up top for the pilot and navigator, with the seat in front guaranteeing a particularly thrilling ride. There was absolutely nothing in front of the pilot except his own feet. The seaplane was about 11.5 feet tall and rested on a large float on bottom, making the whole fuselage look something like 2 canoes connected with piano wire and wooden planks. The aircraft was designed with control and handling components to add to its inherent stability. This was so the plane would appeal to military buyers, as it did to the Canadian government. During the First World War, the Burgess-Dunn became the first military plane Canada ever purchased. But a rocky delivery prevented it from ever getting airborne.
They got to Quebec City, they didn't have time to take the airplane apart. So they put the airplane on the top of the deck and tied it down so tightly that it wouldn't move. Well, if you get in a rolling sea, things had better move or they're going to be in, and it's exactly what happened. At about, I'd say, 100 miles out on a rough sea, and the airplane just broke up.
Nevertheless, the plane's purchase was a triumph of epic proportions for John W. Dunn, who was once believed to be a failure, but will forever be remembered as the creator of the very first swept-wing tailless aircraft. While Dunn's journey of producing his plane was finally coming to fruition during World War I, Geoffrey Hill's journey in the aviation industry was just beginning. While on his honeymoon at the end of the war, he happened to look out onto a pond nearby at seagulls on the water. He couldn't help but notice how the birds could achieve a variety of gliding positions without ever losing control of their wings or flight path. Wouldn't it be ideal, he thought, if an aircraft's wings could adjust to the airflow around it, just like the wings of a bird? He soon got the chance to put his newfound inspiration to the test, and, fittingly enough, it took on the name of a prehistoric bird, the pterodactyl. After a brief stint working as a test pilot, Hill won a 3-year research scholarship, which gave him free rein to develop his ideas. Living just outside Farnborough at that time, he spent his days outside building his very first prototype by hand. His wife, May, also helped out by stitching canvas for the wings and lending her husband a hand when he needed it. One day in 1923, the president of the Royal Aeronautical Society, Colonel Alec Ogilvie, dropped by with a financial vote of confidence for the struggling engineer.
And he came and sat in the kitchen, and he said to Geoffrey, "How are you off for money?" And Geoffrey said, "Pretty short. It's getting pretty short, sir." So Colonel Ogilvie reached in his pocket and produced a £50 note, and that was big money in those days. And he said, will this help?" "It certainly will, sir," my father replied. Colonel Ogilvie said, let me know how you get on, because I want to come and watch you fly it. And Geoffrey said, "Well, there are plenty of other people who might like to fly it." And Colonel Ogilvie said they're all absolutely scared stiff that they're going to be chosen to fly it. And they're unhappy about whether it will fly or not. So Geoffrey said, "Well, we'll see, and I'm prepared to be the first to fly." So that was really the story of the Pterodactyl Mach I.
Hill stayed true to his word to be the first to fly the aircraft. He first got it airborne on New Year's Eve of 1924 and tested it again several times throughout the following year. It was soon ready for the King's Cup Air Show, where the unusual creation caught the eye of both the King and Queen. They thought it was curious that the aircraft looked so much like a bird, and were even more interested to see how it flew. And they weren't the only ones who were impressed when it took to the air. The head of Westland Aircraft at that time was Sir Ernest Petter, who didn't just notice the Pterodactyl because it was oddly shaped, but because it was the one plane in the show with no tail. In almost no time, Hill was named Westland's tailless aircraft designer, and the family moved into a house in Yeovil, which would be their home for the next 8 years. Hill's home away from home would be the Westland facilities, where he was immediately put to work on the Westland Hill Pterodactyl 1A. It was a two-seater monoplane with a greatly streamlined design and a 75 horsepower engine tucked in the back. Over the course of 1926 alone, this aircraft made 21 test flights and could reach a maximum speed of 70 miles an hour. Despite his flying experience, Hill was told by Westland to stay out of the cockpit and instead get back to the drawing board to devise a new and improved Pterodactyl 2, which was designed as a pusher biplane. All of Hill's early models sported wingtip controls that were a combination of ailerons and elevators, namely elevons, which were common on several tailless swept-wing planes in that era.
What they call ailerons on this particular airplane are actually elevons, as there is no tail and no elevator, and the ailerons are back behind the fuselage, so they incorporate the two words and call them elevons. The purpose, of course, is to raise or lower the nose of the aircraft or turn right or left.
The pterodactyls did not use surface controls like ailerons in a normal sense. Rather, they would turn at the end of the wing, which was a process known as wing rotation. Only when both wingtips moved in opposite directions did they function as ailerons. When they moved in the same way, they would work as elevators. This was the secret behind the pterodactyl's remarkable stability and control. In the early 30s came the Pterodactyl 4, which was a 3-seat cabin monoplane with 120 horsepower and a new tandem wheel undercarriage. This model boasted even better control than its predecessors because it was fitted with vertical rudders instead of the usual horizontal rudders. There was also a new gear installed that made it easy to manually vary the aircraft's wing sweep. While Hill was still planning the Mach 5 version, the Air Ministry specification for which the pterodactyls were built was cancelled. Hill paid no mind to this small setback and continued designing. But the seemingly small setback would be followed by a much larger one.
Well, what happened was that Sir Ernest Petter appointed his son Teddy, aged 26, to be technical director, and it led to my grandfather and others resigning. Essentially, from my grandfather's point of view, he felt that it was quite impossible to develop an experimental aeroplane with somebody with so little understanding of what he was doing in charge.
Coincidentally, Hill received an offer from University College London of a professorship in the Department of Mechanical Engineering. He took the job, but remained a part-time consultant at Westland as a favour to Sir Ernest Petter. However, this arrangement ended when he learned of the blow Teddy dealt to the pterodactyl project.
It was Teddy Petter who actually wrote to the War Ministry, as I understand it, to suggest that the pterodactyl program should be scrapped, and so it was. And I think that my grandfather, it was a really bitter blow to him. By that time, he'd really devoted anything up to 15 years of thinking about how to design a plane in this way. And I think he must have felt that it had come to nothing.
Teddy Petter wanted the company to go after more lucrative government contracts, instead of spending time and money on independent research. That decision may have hurt the Pterodactyl, but was a shrewd business move that was ultimately good for Westland. The first specification the company pursued after Teddy took the helm in 1934 was for a military observation plane, which gained notoriety as the legendary Westland Lysander. Now that the Pterodactyl's development was abandoned, Hill dedicated himself to teaching at University College London for the rest of the 30s. But he again got the chance to employ his tailless principles on an aircraft when the British government sent him to Canada for 2 years during the Second World War. The Allies did not have the upper hand in battle in 1942, and the UK felt it needed better technology. So the Ministry of Supply assigned Hill to a glider project at the National Research Council in Ottawa, where he designed and tested another tailless aircraft. Informally called the NRC Pterodactyl Glider, it clocked about 105 hours in the sky by the end of its testing period, and travelled 2,300 miles, clear across Canada. Although Hill was technically based in Ottawa, his work took him all over the continent. In fact, Hill did a lot more than his official job title suggested, and for employers other than the Canadian government.
He was known as the Senior Scientific Liaison Officer. He was very proud of the title because he said it doesn't mean a thing. So I asked him, what did it involve? And he said, well, I go around the different aircraft manufacturers and help them with their sums. Helping with their sums was really a cover-up, because all the time he was working with Boeings, and they were thinking ahead long after the war. Where do we go to from here?
While working with American manufacturers, Hill met another pioneer in flying wing technology, Jack Northrop, and built a solid rapport with the American aircraft engineer. Focusing on the flying wing was a wise instinct for both men, as the high-wing, tailless monoplane style of aircraft was poised to make a comeback. Although Hill's talents were not always appreciated by the aircraft companies in his native land, the Americans were quite taken with his skills and knowledge. This led to a lucrative offer at the end of the war that would have completely changed Hill's professional life.
My mother suggested that Boeing's wanted him to join them as their chief designer at the end of the war, and certainly I believe there were conversations about that, and it was trying to entice, but he would have unlimited travel for him and his family between the UK and Seattle, and of course, had he worked for Boeing's, the world would have been his oyster in terms of his ability to develop ideas. And so inevitably there is a sense, that here was a really remarkable man.
But Hill could not bear to leave Britain for good, even if turning down Boeing was a terrible career move. Upon returning home at the end of the war, Hill was promoted to Dean of the Faculty of Engineering at University College London. By this time, the war was over, but tensions in Europe were still simmering. Germany was still a hotbed for political trouble, and the presence of the Soviet Union in that country did not help the situation. With this in mind, Britain's Ministry of Supply issued requirements in 1947 for an advanced bomber that would protect its interests should the need arise. These requirements, for a very complex and cutting-edge aircraft, were later known as the V-bomber specification. However, the ministry recognized it would be difficult for most manufacturers to quickly fulfill this need. So it also put out a more simple order for a conservative World War II-style bomber that could carry a heavy load and be built much faster. Short Brothers of Ireland won the bid to make this four-engined aircraft called the SA-4 Sperrin. which looked more like a product of the Second World War than a contender to fly in the Cold War. The ministry thought so too, but only years later, when 2 prototypes were already in the works. Shorts was formally told that the Sperrin would not go into production, but its prototypes could still be completed and tested. At about the same time that Shorts was drawing up plans for the Sperrin in 1947, it was also readying itself to relocate to better facilities in Belfast. In addition to taking on the Sperrin, the company decided to also bid for the extremely advanced bomber aircraft that the Ministry of Supply initially ordered. This plane would be the technological opposite of the Sperrin in appearance and capabilities. But the company still needed an expert in aeronautics to help guide the process. Hill's principles were quite well known in the aircraft industry, and Shorts felt he was the right man to call for this job. Despite his distinguished position at UCL, he tendered his resignation and made the move to Belfast. He was technically a consulting engineer for Shorts, but oversaw several projects that others were creating. He also worked closely with chief designer David Keith Lucas, who shared Hill's great interest in tailless plane design. The fuselage of the new aircraft would more or less be modelled after the Sperrin, but the rest of the plane would be far more innovative. They proposed a flying wing configuration, so all the controls would be found on the single wing. Curiously enough, the highly swept wing coincided quite closely with German data for aircraft which could only really maximize the feature at high speeds unobtainable without jet power. By this time, jet power was being employed by at least 4 different countries. With the availability of the jet and ready access to high-speed wind tunnels, Short Brothers used Hill's basic premise of the Pterodactyl, invented almost 30 years previously, to research and design a concept known as the PD-1, a medium-range, high-speed bomber capable of carrying a weight equivalent to those of that era's atomic devices. The wing on this aircraft would still be swept, but would bear differences from the wing that Hill put on the Pterodactyl series several decades before.
Jeffrey called it the isoclinic wing, which meant that you could alter the pitch of the wing at different speeds, that if an aircraft was coming into land, it could have the full use of like a fixed wing, but when it got up high, it could fold it, not completely folded back, but a few degrees, and this would improve the performance enormously.
Short's PD-1 proposal competed with at least 3 other prime contesters, the basically conservative Vickers Valiant, and 2 highly advanced designs, the Avro Vulcan and the Handley Page Victor. Both the Vulcan and the Victor employed German aerodynamic technology, while Short's aircraft was entirely built upon British research of the flying wing. Short's held the title of being the oldest aircraft manufacturer in the world, and was very well respected within government circles and the industry. But on balance, it was ultimately felt that the company's revolutionary design was perhaps a little too revolutionary, and so it was rejected, while the other 3 aircraft went on to form a triad that became Britain's V-bomber force. Not to be deterred, Short Brothers continued privately in 1951 with the development of their 1/3 experimental glider model of the PD-1, which was called the SB-1. This glider was the first aircraft that actually featured Geoffrey Hill's aero-isoclinic wing, and was designed to be an inexpensive machine, which was a good thing, because the only prototype crashed after just a few months of testing. Hill and Keith Lucas went back to the drawing board and emerged 6 months later with an aircraft that essentially sported the same design, but now had a lighter fuselage and 2 small turbojets. The rotary wingtip controls remained, as they would provide this new aircraft with greater stability at transonic speeds. This plane was known as the SB-4 Sherpa, a unique design that could trace its ancestry directly back to the pterodactyls of the 1920s. The Sherpa was first flown in 1953 and ushered in a whole new era of flight engineering. But that wasn't all it represented. This test flight brought with it vindication for Geoffrey Hill, who spent a lifetime trying to prove the worth of the tailless plane and the isoclinic wing. This was a lifetime wrought with personal and professional battles to progress a way of aircraft design that was very much ahead of its day. But as far as Hill was concerned, it wasn't at all about personal glory. It was really only about seeing a good idea get recognized.
I think he never personally pushed himself to be recognized. He would never sort of say, what a good boy am I. No, he was very reticent of taking any personal praise. He would take the attitude that gets in the way of progress.
It seemed the very thing Hill had been waiting for was the Sherpa to touch the sky. When it finally did in 1953, he retired. By that time, the once vigorous engineer found his life was slipping into decline, both in terms of his health and the way he was regarded in the aviation industry.
A story that sort of encapsulates this was told by Harold Penrose, again the chief test pilot at Westlands, in I think it was 1954-55, at the Farnborough Air Show. My grandfather always had a drinks party to which he invited all his old friends and so on. And Harold Penrose was running very late for getting there, but eventually got there and was very dismayed to find that there were no cars in the driveway. Anyway, he rang the bell. My grandmother answered it, and he said, "I'm so sorry, I'm late for the drinks party." And she said, "Nobody came, and Geoffrey's gone upstairs to bed, but he'd love to see you." And that was the last time that Harold Penrose saw my grandfather before my grandfather died.
In many ways, it could be said that Hill was a disappointed man when he died in 1955 at the relatively young age of 60. For such a prolific engineer and designer, none of his planes ever made it into production, not even the Sherpa, which was only ever meant to be an experimental aircraft. Moreover, the project he had devoted most of his young life to, the Pterodactyls, was cut short before reaching fruition. But at the same time, Hill's goal was finally realized as the Sherpa first graced the skies in 1953. Although it was never a V-bomber, it proved the performance value and stability of the tailless plane, and truly showed the world the importance of the aero-isoclinic wing. And although Hill was never a celebrated designer, it can't be denied that his work altered the flight path of aviation.
The F-12, Trisonic Long-Range Improved Manned Interceptor. Capable of sustained supersonic cruise at more than 2,000 miles per hour. A two-man crew, pilot and fire control officer, fly at altitudes above 70,000 feet in a combat radius greater than 1,200 nautical miles. The airframe and engine design are optimized for Mach 3 flight. The titanium airframe surviving temperatures in excess of 600 degrees Fahrenheit. The two J-58 engines, producing 65,000 pounds combined thrust, equal to 4 Century Series fighter engines. Airborne, the F-12 acts as a freelance hunter-killer. The autonomous ASG-18 fire control system, a pulse Doppler clutter-free display designed to operate in any ECM environment, is backed up by 3 Block 3 AIM-47As with an aerodynamic range 20 times greater than present air-to-air missiles. An onboard computer guides the pilot to a collision course in the horizontal plane. The fire control officer monitors a self-contained inertial navigation system, feeding constant positional information to the computer. The horizontal tactics indicator displays interceptor-target relationship in an extrapolated attack, acts as a navigation aid, and provides self-test instructions for the fire control system.
Missile preparation completed. Missile is good. Have good tracking, range 75 miles. Max on launch range in 40 seconds. Roger. The dot is set. Well to fire, special weapon enabled. Roger. Switches are on. Roger. Range 45 miles. Firing now.
Designed to fire at the F-12's optimum cruise altitude with only gross steering required by the pilot, the semi-active pulse Doppler guided missile with conventional or nuclear warhead speeds on a collision course at Mach 6. Aerodynamic range, 100 nautical miles. Sea level to 100,000 feet. Maneuverability, 22 Gs. Up, down, right or left. Complementing the radar is the infrared search and track subsystem. Infrared energy is gathered at long range, allowing early detection of supersonic targets.
IR target confirmed. Better check on our commitment. Army Control, this is Alpha X-Ray 02. Have an IR target 30 degrees left. Should we hit it?
Alpha X-Ray 02, that is affirmative. Freelance approved. We'll have a subsonic track for you within 10 minutes.
The F-12's ability to act as a free agent or respond to precise ground control, combined with its speed and maneuverability, give it a multiple commitment capability over a wide area of NORAD. Worldwide, the F-12 can fly across the Atlantic without refueling in little more than 2 hours. From the United Kingdom, its combat radius covers all of Europe. For Far East deployment, F-12s could make the 7,200-mile trans-Pacific flight to the Philippines in 5 hours with just 2 refuelings and be effective in combat over a wide area. The YF-12A has been flying successfully for a number of years, logging several hundred hours. Even better performance can be expected in the production model. The airframe is a duplicate of the SR-71, an outgrowth of the original YF-12A program. Removing ventral fins and extending chines forward improve aerodynamic stability, increase fuel capacity, and gross takeoff weight. Additional fuel and improved engines extend the ferry range. Payload is increased to 4 missiles. Folding fins allow internal installation, and a trapeze rail launcher permits checkout of 85% of missile functions before launch. A new antenna provides significantly more detection range, more than 100 nautical miles against a medium bomber target. And infrared system performance is improved. The F-12, holder of 9 world records, truly represents a giant step forward in aircraft technology and performance. The first titanium airframe, first sustained supersonic cruise, first pulse Doppler clutter-free radar, and a fire control system designed to operate autonomously. With long-range, highly maneuverable missiles fired from optimum cruise altitude at trisonic speeds in a performance envelope many times greater than our present capability, the F-12 stands ready today to meet the air defense needs of the 1970s and beyond.
In the early years of the Cold War, with military airfields deemed vulnerable to Soviet missile attacks, the concept of underground airports gained traction among Western governments. The rationale was that subterranean bases would offer better protection against enemy assaults and could potentially serve as hangars and launch sites for future stealth aircraft. However, the development of underground airports required the simultaneous creation of high-speed aircraft with vertical takeoff and landing VTOL capabilities, as traditional jets rely on runways and open skies for takeoff. One early attempt to build such an aircraft was made by the Canadians. The Avrocar emerged from a series of blue sky research projects led by designer Jack Frost, who joined Avro Canada in June 1947 after gaining experience with several British firms. At the time, Frost was particularly focused on jet engine design, seeking ways to enhance the efficiency of the compressor without complicating the simplicity of the turbine engine. During the 1950s, Jack Frost initiated the ambitious Project Y, with the aim of developing a vertical takeoff and landing aircraft capitalizing on his newly designed high-power engine. This project represented a forward-looking exploration into VTOL capabilities, aligning with the broader interest in unconventional aircraft designs during the Cold War era. The innovative design featured the redirection of thrust through ducts along a distinctive delta wing, reminiscent of a spade on a playing card. Despite encountering financial constraints and skepticism from the military, Frost persevered in his experimentation. He explored the Quanda effect to enhance the VTOL capabilities, seeking a more practical solution for the project. Although Project Y secured funding from the Canadian Defence Research Board and the US, the Avrocar, a project initiated by designer Jack Frost at Avro Canada, faced eventual cancellation due to safety issues encountered during testing. The concept of the aircraft went beyond conventional boundaries, aiming to create a supersonic large-disk fighter with the unique capability of performing vertical takeoffs and landings. The project reflected the era's challenges and aspirations in pushing the limits of aeronautical innovation. To gather flight data on the basic concept while engine development continued, Frost proposed the construction of a smaller proof-of-concept test vehicle in 1958, which he named the Avrocar. Simultaneously, the US Army was engaged in various experiments involving smaller vertical takeoff and landing aircraft, envisioning them as flying jeeps. The Army became interested in Avro's concept, and Frost pitched the smaller design as a prototype suitable for the Army's needs and an aerodynamic testbed for the WS-606 engine. Initial performance requirements for the Avrocar included a 10-minute hover capability in ground effect and a 25-mile range with a 1,000-pound payload. Avro secured a $2 million joint services contract for the construction and testing of 2 Avrocars, designated by the Army as VZ-9AV. The Army expressed significant interest in the Avrocar program, considering it a potential replacement for helicopters. However, safety concerns during testing eventually led to the cancellation of the project, highlighting the difficulties in realizing unconventional and ambitious aircraft concepts during that period. Additional Air Force funding, approximately $700,000, was allocated to the project from the 606A program. In March 1959, a $1.77 million contract was secured for a second prototype. Despite setbacks, including the cancellation of the Avro CF-105 Arrow program in 1959, the Special Projects Group at Avro Canada continued its work on the Avrocar, with renewed involvement from company leadership. The USAF Project Office initially recommended cancelling the WS-606A and related work, but an extensive effort led by Jack Frost resulted in the authorization to continue the Flying Saucer programs in May 1959. The Avrocar, notable for its disc-shaped design reminiscent of a frisbee, featured an 18-foot diameter and a thickness of 3.5 feet. Supported by a robust equilateral triangle truss, its distinctive element was the 124-blade turbo rotor, centrally positioned and powered by 3 Continental J69 T9 jet engines. The airframe, predominantly constructed from aluminum, had an empty weight of 3,000 pounds. The initial undercarriage included 3 small cast-steering wheels, later replaced by skids during testing. Piloting the Avrocar involved a single-side mounted control stick, enabling conventional pitch, roll and yaw control through adjustments in airflow. The attitude thrust control system, positioned outside the main disc, facilitated changes in vertical lift and directional control. To counteract inherent instability during forward flight, a mechanical stability augmentation system was implemented. The Avrocar's unique design and control mechanisms aim to address the challenges of achieving vertical takeoffs and landings while ensuring stability during different flight phases. Leveraging the turbo rotor's significant angular momentum, it functioned as a powerful gyroscope, stabilizing the craft. The crew compartment accommodated 2 individuals in separate cockpits integrated into the airframe. Practical testing initially involved a single pilot, with occasional flights featuring an observer in the secondary cockpit. Addressing control intricacies, Avro test pilots honed a nuanced understanding of the craft's sensitive inputs. Chief Development Test Pilot Petocci achieved a hands-off flight after resolving control issues, marking a notable advancement. However, despite progress, Avro test pilot Peter Cope, USAF project pilot Walter J. Hodgson, and NASA's Ames Research Center Chief Test Pilot Fred J. Drinkwater III all emphasized the persistently challenging nature of the Avrocar. Drinkwater likened flying it to balancing on a beach ball. The first Avrocar, 587055, faced hover issues due to exhaust mixing and limited lift, leading to modifications. The second, 594975, encountered uncontrollable roll and pitch oscillations during tethered hover attempts, attributed to the hubcapping effect, prompting numerous modifications. Despite improvements, nozzle control issues and stability problems persisted. A new design with separate hover and forward flight controls in 1960 demonstrated better control but maintained pitch instability. Further modifications in 1961 improved hover control, allowing speeds up to 100 knots, but pitch instability persisted. A second evaluation in June 1961 revealed control problems and limited flight above critical altitudes. Before modifications could be implemented, funding ran out in March 1961. Despite Frost's proposals for a modified design, the Avrocar and related WS-606A supersonic VTOL programs were officially cancelled in December 1961 by the US military. The VZ-9AV Avrocar and its nascent VTOL technology are credited with paving the way for the development of subsequent VTOL-capable aircraft, such as the AV-8B Harrier II, V-22 Osprey, F-22 Raptor, and others currently employed in various missions by the US military. Despite its challenges, the Avrocar played a significant role in advancing vertical takeoff and landing technology, contributing to the evolution of modern VTOL aircraft.
Produced by Avro Aircraft Limited at Malton, Ontario, the Avrocar symbolizes the culmination of the second stage of an extensive program of research in the field of disk flight. Two identical vehicles were built for the purpose of conducting static tests, full-scale wind tunnel tests, and flight tests. Wind tunnel tests were performed at Ames Research Center, California, and static and flight testing was carried out at the Avro Test Facility near Toronto, Canada. For static testing, a rig was constructed to support the vehicle at varying heights above the ground. Strain gauge dynamometers at the three attachment points permitted lift and side forces to be measured throughout the program. Instrumentation, control, and fire extinguishing lines were installed from the vehicle to the adjacent control room. A remote fuel supply minimized the fire hazard. The first vehicle, completed in May 1959, was installed in the rig for an extensive series of static tests before being dispatched to Ames Research Center for wind tunnel testing. Initially, the vehicle was operated from the control room, where remote instrumentation recorded engine and turborotor performance, duct pressures and temperatures, and spoiler control positions, permitting comparison between theoretical and actual results. Static testing extended over a period of 5 months, during which time 32 hours of testing were performed without failure of any major component. Minor modifications, proved desirable by analysis of early test data, were introduced both into the test vehicle and into the second vehicle now nearing completion. Typical of these was the modification of the exhaust boxes to improve temperature distribution and introduction of a cascade beneath the turborotor to improve duct flow. The engine inlets were also modified to breathe from the upper skin in order to reduce high inlet temperatures experienced in early tests with the engines breathing from the internal ducts, and further tests were then performed. Introduction of these modifications enabled operation of all engines at full power. Tufting on the underside of the vehicle was used to provide visualization of the focus jet. Later in the program, the remote controls were replaced by the actual cockpit controls. It was now possible for the first time for the pilot to check performance and control characteristics with the vehicle in the flight configuration. Data obtained from oscillograph traces which recorded moment, lift, and center of pressure with variation of control position during static tests was punched onto IBM cards and fed into the IBM 650 computer. The output cards from the computer were then plotted to provide control characteristic curves. Using this data, control system problems were accurately simulated on the analog computer. The aircraft cockpit and pneumatic control system were reproduced using a compressed air supply in place of engine bleed air. The effect of control system modifications was also investigated before changes were made to the test vehicle. As testing of the first vehicle continued, manufacture of the second Avrocar was completed. Preparation was made for the initial engine run, and for this test, the vehicle was secured by cables attached to each landing gear leg. This tie-down arrangement permitted checking of the engines at power settings in excess of the unstick setting, and also provided an opportunity for instrumentation and controls to be checked prior to tethered flight. Subsequently, the test was repeated with the vehicle raised on jacks in order to determine the effect of height on engine inlet temperatures, which were believed to increase due to recirculation of exhaust air. Tethered flying commenced with the vehicle restrained by 3 cables attached to the hoisting lugs and to anchor points in the concrete apron. During testing, the temperatures of critical items of equipment were recorded in the control room. Intercommunication between the pilot and the control room permitted monitoring of the tests by the flight test engineers. An alternative system of tethering, in which the vehicle was restrained by weight rather than by rigid anchor points, was then employed. Some difficulty was still experienced in controlling the vehicle, due partly to the influence of the tethers and partly to loss of lift with control application, which had also been experienced during static tests on the first vehicle. The control system was modified and the vehicle installed in the test rig with the upper nozzle closed except for 4 20-degree segments at the cardinal points. Tests were conducted with different central jet arrangements and various spoiler configurations. Meanwhile, after 32 hours of static testing, the first vehicle was being inspected and overhauled in preparation for the wind tunnel test program. Instrumentation specified for the program was also installed. Finally, the vehicle was crated in preparation for shipping from the Avro plant at Malton to Ames Research Center in California. Rig testing of the second vehicle continued, and the addition of extension links permitted the vehicle to be tested at different heights above the ground, and also allowed application of pitch during testing. These tests indicated some improvement in control characteristics, and the vehicle was returned to the tethers, where static test results were confirmed, although the tethering cables continued to introduce random inputs, making accurate assessment of stability and control difficult. Sufficient data had, however, been recorded and analyzed to indicate that operation without the tethers was now possible. On November 12, the Avrocar made its first free flight. In free flight, the vehicle showed a marked reduction of the oscillatory tendency experienced in the tethers. Control sense was correct, although more control power and less lag was obviously required. The number of control sectors was increased from 4 to 6, and after a further period of static testing, the vehicle was prepared for free flight in this configuration. With the increased control power provided by the 6-point system, the behavior of the vehicle was much improved. Stability within the ground cushion was better than before, and the gyro-stabilizing effect of the turborotor was now apparent. Although several satisfactory flights were made, it was realized that one characteristic of the spoiler control system in particular was compromising the performance of the aircraft to a greater extent than had been anticipated. Application of control reduced lift on one side of the aircraft with no corresponding increase on the opposite side. The ideal system would be one which would move the focal point of the jet without loss of lift. A system providing these characteristics had been designed and was being tested on the 1/20th scale model. A focusing control ring around the lower periphery of the vehicle replaced the spoiler control and deflected the jet to provide both control and forward thrust. Static test using steam provided flow visualization of focusing ring control operation both in free air and near the ground. Static and forward flight force tests were performed in the Avro wind tunnel, and flow visualization tests were also performed in the forward flight configuration. After successful completion of model tests, the system was installed in both vehicles. A further period of development in the static rig was required to check the characteristics of the new control system before flying continued. Most of the effort during this period was devoted to achieving a system in which the power required to operate the focusing control ring was compatible with the pneumatic power available from pilot and gyro stabilizer inputs. Tethered and free flights which followed were directed toward increasing the stability of the vehicle in the ground cushion and increasing the stable height of the ground cushion. Development of the new control system resulted in a marked improvement in attitude stability, control sense, and response rate. At a height of 3 feet and at forward speeds up to 20 knots, the vehicle no longer displayed the previous tendency to oscillate after pilot inputs, and short, stable flights with hands off were now possible. The height at which the ground cushion tends to become unstable, now known as the critical height, was found to occur at the point where the simple annular jet formed near the ground changes to the focus jet formed at increased height. Any change of attitude with the aircraft at this critical height causes the jet to become focused on the upgoing edge while remaining unfocused on the downgoing edge with resultant hysteresis. An additional, more powerful central jet was added to improve ground cushion stability. It was found, however, that an increase in ground cushion stability was accompanied by a decrease in control power, and the final configuration represented a compromise between the two requirements. Tests were also performed to establish the stabilizing effect of the gyro stabilizer, and it was determined that signals resulting from small changes of attitude were being lost due to system friction and control ring hinge moment. It was apparent at this point that some form of assist was required to transmit stabilizing signals from the gyro to the control ring, and design of a pneumatic booster was commenced. At Ames Research Center, the first vehicle was now ready for installation in the 40 by 80 foot subsonic tunnel. Here, tests would be performed to determine the transition trajectory from hovering both in the ground cushion and in free air. These tests were all performed using the focusing ring control system, which had resulted in the most successful free flights on the vehicle at the Avro test facility. The variable mount permitted testing to be carried out at heights up to 12 feet. Flight tests on the second vehicle were discontinued to permit introduction of the pneumatic control boost system. This involved the introduction of 6 sensing nozzles at the base of the central control shaft to monitor 6 pneumatic actuators mechanically connected to the control ring. The base of the shaft was now secured by a flexure, and only a small travel was required to transmit gyro-stabilizing signals to the actuators operating the control ring. Functional and frequency response tests were carried out with the pneumatic system pressurized from an external supply. A variable speed mechanical shaker was used to excite the control column, and measurements of control ring motion were made using potentiometers connected to a continuous trace recorder. Subsequently, the tests were repeated with engines operating and the system pressurized by engine bleed air. Tether tests were performed to permit final checking of the power-boosted control system before free flying was resumed. Flights with the pneumatically boosted control system showed a marked improvement over the previous configuration. Stabilizing signals from the gyro were now quite apparent. The pilot reported that the feel of the aircraft was better with the new system, and that precise positioning without excessive effort was now possible. In summary, development of the vehicle resulted in a gradual improvement from the relatively unstable first flight requiring rapid pilot inputs through various applications of the spoiler control system, which was abandoned due to lift loss with control application, and ultimately to the introduction of the focusing control ring, which resulted in the most significant improvement to date. In the most recent configuration, with the addition of the pneumatic control boost, the vehicle displayed stable flight characteristics at a height of 3 feet and at speeds up to 30 knots. The wind tunnel test data showed, however, that the focusing ring control, though it had been developed for satisfactory hovering, was not good enough for forward flight, and that fairly extensive modifications were required to add an improved forward flight control system. Testing was therefore discontinued until the two vehicles could be modified in readiness for further wind tunnel and flight test programs.
XF-92A Convair Model 7002 is a research airplane, a part of the XF-92 program. It is presently being flown at the U.S. Air Force Base, Muroc, California. The purpose of these flights is to gather data concerning the characteristics of a new configuration designed to meet the requirements of an interceptor fighter operating at transonic and supersonic speeds. Extensive study and research by Convair engineers some time ago led to the conclusion that the best aerodynamic configuration for this type of operation was one utilizing a 60-degree delta wing. The wing planform promised several major advantages. First, low drag at transonic and supersonic speeds. Second, smooth handling characteristics and freedom from buffeting at transonic speeds. Third, satisfactory low-speed handling characteristics. And fourth, a structural form ideal for attaining high rigidity, lightweight, and simplicity. Numerous tests of models in wind tunnels and in free flight have confirmed these conclusions. Full-scale confirmation, however, is essential. The Model 7002 airplane was constructed to obtain these full-scale data. It has a 60-degree delta wing and a similar vertical surface. The airplane is powered at present by a single J-33A-23 jet engine with 5,400 pounds thrust for takeoff. Although this is less thrust than is obtained from more recent power plants, it does permit exploration of the airplane's characteristics at high subsonic speeds in level flight. Still higher speeds are obtained in dives. To establish correlation between theory and practice with this new wing planform, a flutter study is being conducted as a part of the program. A major problem in the design of all aircraft capable of transonic speeds is that of providing satisfactory control forces. The 7002 utilizes a 100% hydraulic boost system with no feedback. The pilot senses stick forces which are produced by an artificial field system. Forces are made to vary automatically with airspeed. Pilot comments during flight tests are taken on a wire recorder. An oscillograph and movie photo panel installed in instrumentation compartments comprise the other principal means of recording test data. Perhaps the most outstanding characteristic of the 60-degree delta wing is the low drag rise encountered at transonic speeds. A comparison of the increases in drag coefficient of conventional swept-back wings and that of a 60-degree delta wing near Mach 1 is presented here. The maximum value of the drag coefficient C sub D for the conventional wing is approximately 4 times that of the delta wing. Even more significant is a comparison of thrust requirements in the transonic and supersonic speed ranges. It will be noticed that the difference in speed between the 35-degree swept wing and the 60-degree delta wing is small at the lower values of thrust. However, at the higher thrust, representative of future power plants, the advantage of the delta wing becomes very impressive. Airplanes with conventional tail configurations experience a reduction in elevator effectiveness on approaching Mach 1, whereas a delta wing with integral control surfaces does the opposite. This means that the maneuverability of delta wing aircraft will not be objectionably diminished at transonic and supersonic speeds. Another advantage of the delta wing is that gusts produce lower structural loads. Presented here in graphical form are comparisons of the effects of negative and positive gusts of two intensities. Flight at supersonic speeds with the best turbojet power plants now being developed is practical only when wing thickness ratios are 5% or less. At 5% thickness, the wing weight per square foot of a delta wing is less than half that of a conventional wing with sweep back. Simplicity of construction inherent in the delta configuration is demonstrated by a comparison of the aerodynamic control surfaces required. The controls in the pilot's compartment are conventional. Elevons form the wing trailing edge and move up and down together to produce elevator action when the stick is moved fore and aft. When the stick is moved from side to side, one elevon moves up, the other down. This provides aileron action. Pedals control the rudder, which operates in conventional manner. Initial flight of the 7002 was made at Muroc Air Force Base in the latter months of 1948. In such testing, precise scheduling of operations is required. Other test projects utilize the same facilities. Coordination of all test activities is performed by the Air Force. Before the airplane is taken from the hangar, film is inserted in the instrument recording cameras, batteries are charged, and numerous other items are serviced or inspected. In order to have full tanks for flight, the airplane is towed to the runway before the engine is started. The pilot, flight inspector, and other project personnel necessary to the performance of a flight leave for the runway. Air-to-ground radio communication is maintained throughout test flights. A radio truck receives and transmits pertinent information to observers spaced along the runway. Wind velocity and direction are measured immediately before takeoff. Prior to the first extended flight, a number of high-speed taxi runs and straightaway flights just off the runway were made to provide data for adjustment of the control sensitivity. These runs allowed the pilot to become familiar with the airplane's handling characteristics and to develop the technique of flying at the high angles of attack associated with low aspect ratio wings. The first tests were conducted on the 7-mile lake bed runway. Subsequent flights have been carried out from time to time on the main concrete runway and the shorter lake bed runways. The combined efforts of the Air Force, the NACA, and Convair have been devoted to the launching of this new type aerial weapon. The first takeoff is uneventful. A chase plane is used to make close-up visual and photographic observations of the airplane and its behavior in flight. The two pilots maintain contact by radio. Movie cameras within the fuselage record control movements, airplane attitude, throttle setting, speeds, pressures, temperatures, in short, every aspect of the flight. Approximately 1,500 pounds of instrumentation is carried. This represents more than 10% of the airplane's gross weight. The gross weight at takeoff is about 13,500 pounds. The fuel burned in a 30-minute flight reduces the weight to 12,000 pounds for landing. Completion of the first flight marks the beginning of a period of adjustment, calibration, and research testing. Records must be removed, reproduced, and studied before another flight. The study, planning, and preparation of instrumentation for each flight takes much more time than the operations connected with flying. Limited tests to date show lower drag and higher performance than predicted. Difficulties encountered up to the present time all appear to have reasonable solutions. No problem has yet arisen which compromises the basic advantages of the delta wing configuration. This airplane is the one design now flying in which a pilot can operate transsonically with no undesirable aerodynamic disturbances. With the inherent low drag and good aerodynamic characteristics at transonic and supersonic speeds, the Air Force now has a weapon which can be developed tactically with confidence.
Throughout the 1950s, major aircraft manufacturers in the United States were eagerly exploring the potential of vertical takeoff and landing (VTOL) technology across various military applications. With the looming threat of intercontinental ballistic missiles and thermonuclear weapons, the military sought VTOL aircraft capable of operating from small dispersed sites without relying on traditional air bases or aircraft carriers, targets that were increasingly vulnerable to attack. A key concept driving this pursuit was the notion that an aircraft with a thrust-to-weight ratio exceeding 1 could vertically launch, transition to horizontal flight for mission execution, and then return for a vertical landing. Such capabilities promised to eliminate the need for expensive and easily targeted runways, enhancing the aircraft's survivability and operational flexibility in a rapidly evolving strategic landscape. Among the pioneers in this endeavour was the Ryan Aircraft Corporation, which endeavoured to translate this concept into a practical fighter aircraft for the Air Force with its X-13 Vertijet. However, like most other VTOL aircraft, the performance compromises made for their unique capabilities did not warrant its introduction in place of more capable conventional aircraft. The idea for the Vertijet originated just after World War II, when engineers for Ryan casually debated whether or not their FR-1 Fireball, which had a thrust-to-weight ratio of 1 at low fuel quantities, could take off vertically. The vertical takeoff idea soon advanced beyond the discussion stage. In 1947, the Navy's Bureau of Aeronautics enlisted Ryan for a contract aimed at exploring the technical complexities associated with developing a vertically launched jet fighter, a pivotal aspect of a broader initiative to assess the viability of submarine-based aircraft. Concurrently, the Navy funded a series of experimental tail-sitter aircraft comprising conventionally configured planes outfitted with large counter-rotating propellers designed to rest vertically on reinforced tail sections. Notable examples included the Convair XF-Y1 and Lockheed XF-V1, intended to utilize their high-thrust propellers for vertical takeoff from various naval vessels, thereby furnishing defensive air cover without the need for aircraft carriers. Ryan's engineering analyses demonstrated the feasibility of a comparable jet-powered design, augmented by a reaction control system capable of redirecting exhaust gases to facilitate control during hovering and low-speed flight. Subsequently, a Navy contract facilitated the construction of an unmanned flying prototype, which conducted its inaugural flight on October 20, 1950. This peculiar contraption, affectionately dubbed the Beast in the Backyard, was propelled by an Allison J-33 turbine and employed a ball-mounted nozzle to provide reaction control while hovering. Ryan engineers converted a B-47 fuel tank into a cockpit to allow test pilot Peter Girard to evaluate the testbed's suitability as a manned research aircraft, which sat on its tail to take off vertically. On November 24, 1953, Girard made the first manned hovering flight in a jet aircraft with this unusual machine. After Navy funding ran out, the Air Force became interested in Ryan's experiments and in July 1954 issued a contract to the company to construct 2 VTOL tail-sitter demonstrators designated as the X-13 Vertijet. This project, based on the earlier Navy design proposal, was to demonstrate the suitability of easily dispersible VTOL fighters. Under the guidance of Chief Engineer Curtis Bates, the X-13 emerged as a compact, single-engined delta-wing fighter, with its distinctive features being a set of winglets and fixed landing gear, elements that might appear ordinary to the casual observer. Spearheaded by Robert Furman and the Ryan Technical Section, the aircraft was meticulously designed to be transported on a specialized trailer, capable of tilting vertically to facilitate the launch and recovery of the X-13 during vertical takeoffs and landings. In late 1955, Ryan successfully completed the first Vertijet, serial number 541619, and on December 10th, Girard piloted its maiden flight. Initially equipped with a fixed tricycle landing gear, the X-13 underwent testing as a conventional aircraft. Furman and his team prioritized exploring the conventional handling characteristics before risking vertical flight testing. Following the resolution of oscillation issues through the installation of dampers, engineers affixed a temporary steel tube truss with clustering wheels to the rear of the X-13. This modification allowed the aircraft to assume a tail-sitting position during vertical flight testing, eliminating the need for the complex launch and recovery procedures associated with the launch trailer. Pete Girard made the first vertical takeoff and landing on May 28, 1956. On the same day, the second X-13 made its first flight. The aircraft was agile and responsive in conventional flight. As the aircraft transitioned to a nose-high attitude to achieve a hover using the thrust from its own engine, a vectorable exhaust nozzle linked to the controls provided a straightforward and efficient means of control. To facilitate the delicate landing process, small bleed air thrusters positioned on the wingtips enabled minor adjustments to the pitch and yaw of the aircraft when necessary. Integrating both conventional and VTOL control systems, a stability augmentation system ensured smooth transitions without requiring abrupt changes to pilot control inputs. During vertical takeoff, the launch procedure involved raising the bed of the launch trailer vertically. This allowed the X-13 to hang from a cable suspended by 2 arms on the top of the trailer, featuring a partially retractable hook. For vertical operations, flat bumpers replaced each of the main wheels on the fixed landing gear, preventing damage to the fuselage underside if it swung into the trailer bed, thereby facilitating transportation. Subsequently, the pilot would increase throttle until the hook lifted off the launch cable, then maneuver away from the trailer and accelerate vertically, smoothly transitioning to conventional flight. However, vertical landings posed greater challenges and were perhaps the most impractical aspect of the Vertijet concept. Its primary drawback, akin to earlier tail-sitters, lay in the obstruction of the pilot's vision by the airframe, making it exceedingly difficult to accurately gauge the distance to the ground without external assistance. Although the pilot's seat pivoted 45 degrees towards vertical during landing, the pilot still had to approach the recovery trailer blind, with the underside of the fuselage facing the surface of the trailer. Constant radio communication with a ground observer was essential to talk the X-13 into position during the cumbersome process. A 6-meter, 20-foot long folding pole with marked gradations attached to the top of the recovery trailer gave the pilot a clear indication of the distance remaining before he contacted the trailer. Once in position, the pilot gradually reduced the throttle until the nose hook caught the recovery cable. On May 28, 1956, the X-13 executed its inaugural vertical hovering flight, initiating a series of summer tests where Girard and fellow test pilot Lou Everett practiced cable catching techniques using a 1-inch thick rope strung between 2 towers. To safeguard against potential damage during docking maneuvers with the trailer, Ryan engineers equipped the X-13 with a replaceable wooden nose. On November 28th, Girard accomplished the first ever transition from horizontal to vertical flight and vice versa in the X-13. Then, on April the 11th, 1957, he launched from the trailer, seamlessly transitioning to conventional flight, and executed a vertical landing, successfully fulfilling the X-13's mission profile. Illustrating the concept of dispersed operating sites, the second X-13 captivated over 3,000 military officers and journalists with an impressive display at the Pentagon on July 30th, 1957. However, competing programs diverted funds away from the project, leading to the X-13's final flight on September 30th, 1957. Despite later programs like the XV-6 Kestrel and the AV-8 Harrier achieving operational success, the X-13 provided an effective solution to the challenges of developing a VTOL fighter within the technological constraints of its era. The Vertijet successfully completed all designated tasks and undoubtedly excelled as an experimental demonstration aircraft, despite the inherent impracticality of the operational concept. Ironically, by the close of the 20th century, the thrust vectoring system, originally pioneered on the X-13, would evolve into an indispensable component of advanced combat aircraft. In 1960, Ryan generously donated the first X-13 along with its launch trailer to the Smithsonian Institution. Originating from a design philosophy dating back to 1930, but conceived during the Second World War, the XCG-16 Glider emerged as one of the most unconventional and innovative glider concepts ever tested. Initially designed for transporting heavy equipment and supplies, including vehicles and military personnel, the XCG-16 later became involved in experiments to deliver fuel to long-range bombers during flight. As a crucial element of the war effort, it showcased the capability to transport substantial loads without the need for an engine. Despite its troubled test history and eventual exclusion from production, the XCG-16's design retained its distinctive features. The roots of the XCG-16 can be traced back to May 1930, when American aero engineer Vincent Bernelli explored various lifting theories and flying wing concepts. The United States Army Air Force subsequently issued a specification calling for a novel design incorporating Bernelli's patented lifting fuselage concept. To assess the most suitable design for military use, a competition among different aircraft manufacturers was organized at Wright Field. Designers Hawley Bolus and Albert Kriz utilized Bernelli's concept as a foundation to create their own glider for the competition. Bolus, previously focused on designing leisure aircraft and recreational vehicles for the civilian market, ventured into military aircraft design for this competition. His most notable design had been the Bolus Road Chief, the trailer and caravan upon which Airstream had based their famous design. He'd also worked as one of the consultants on the Spirit of St. Louis, the aircraft piloted by Charles Lindbergh, who completed the first non-stop transatlantic flight between New York and Paris. Despite lacking experience in combat and military design, Bolus moved forward with his concept, collaborating closely with Kriz and the team at his company, Bolus Sailplanes. The German military's successful use of gliders during the 1940 invasion of Belgium, particularly in landing troops in challenging areas behind Belgian lines, drew attention. Gliders played a crucial role in capturing strategic sites, exemplified by the rapid overrun of Fort Aben-Amal in May 1940, where glider-borne Nazi soldiers surprised Belgian troops. While the United States initially maintained neutrality in the early stages of the war, experiences like the Battle of Fort Aben-Amal prompted the United States Army Air Corps to take gliders seriously into consideration. In response to the USAC's request for a glider capable of transporting troops, heavy equipment, and supplies towed behind engine-driven bombers and transport planes, Bolus and Kriz diverged from the traditional single fuselage design that characterized most American gliders. Instead, they embraced a flying wing concept, closely studying Bernelli's philosophy and incorporating their own ideas on top of it. A half-size prototype model was created in late 1942 by Bolus Sailplanes, with Bolus and his team considering the initial test results to be good. The first full-size glider prototype, named the MC-1 glider, was produced by General Airborne Transport. Following the closely followed design of the half-size model, initial factory tests once again indicated the potential of the new design. The full MC-1 design was envisioned to be larger than other gliders of its time. It was characterized by a high wing configuration with a wooden frame and fabric covering, all while retaining Bonelli's philosophy. With a wingspan of 110 feet and a length of 67 feet, the MC-1 boasted substantial dimensions. Bolus aimed for a cargo capacity of up to 15,000 pounds, facilitating the transport of both cargo and troops through two large cargo doors located at the glider's front for easy access and rapid deployment during battle situations. The intended operational method involved towing the XCG-16 into the air by a C-47 or C-54 Air Force transport plane, which would then release the glider to continue its flight independently. The glider featured a twin boom design for the tail. Designed with spoilers, the XCG-16 could deploy them to reduce lift and increase drag, enabling rapid descent and short landings on various terrains. Additionally, the glider was equipped with retractable landing gear, deployable for landings on rough ground. The maiden flight test of the MC-1 began on the 19th of July 1943 at March Field, California. The first test run proved to be a success and was commended by military and business observers. A second test flight was scheduled at March Field on the 11th of September 1943, but this run ended in disaster. Among the crew and passengers aboard the glider were notable aviator and businessman Richard Chichester DuPont and military glider specialist Colonel Ernest Gable, who was set to pilot the MC-1 for its demonstration. During the demonstration, the glider was towed by a Lockheed C-60. Shortly after takeoff, an unintended encounter with the C-60's prop wash caused the glider to violently sway from side to side. Compounding the issue, the weight ballast inside the glider had not been properly secured and began to shift, exacerbating the rapid tilting of the XCG-16. Recognizing that a crash landing was imminent, 3 of the passengers, including DuPont, attempted to parachute from the glider as it continued its descent. While 2 passengers successfully landed safely, DuPont tragically lost his life when his parachute didn't open in time. Colonel Gable remained on the glider and also lost his life when it ultimately crashed into the ground. Despite the tragic setback at March Field, Bolus continued with the design, and the US military awarded a contract to the General Airborne Transport Company in November 1943 after negotiations. The contract approved the construction of 3 MC-1 units. 2 flyable and 1 for static tests were awarded by the USAF. The completed full-sized MC-1 gliders were also given the military designation XCG-16, and the name stuck. Only 1 completed XCG-16 unit was manufactured and submitted for USAC testing. Test pilots and engineers acknowledged the XCG-16's strong aerial performance, highlighting its excellent stability and maneuverability. However, military observers concluded that the glider fell short of expectations in terms of cargo and loading capabilities, deeming it unsuitable for combat situations. Consequently, no additional units were produced. There was initial consideration of repurposing the glider for new Air Force experiments. In 1944, the US military explored the concept of extending the range of existing transport and bomber aircraft by utilizing trailing gliders to carry fuel. The XCG-16 airframe was handed over to the Cornelius Aircraft Company, known for building gliders, to modify and test the forward-swept wing design, capitalizing on the XCG-16's robust capabilities. The Cornelius Company made several alterations to the glider, renaming it the XFG-1 and prepared it for a test flight. However, the first XFG-1 model crashed during a demonstration in October 1944. Although a second model was produced by Cornelius following the Bolus format, by that time the US military had lost interest in the project, leading to the discontinuation of further development. The Ryan XV-5 Vertifan was an experimental jet-powered VTOL vertical short takeoff and landing aircraft developed in the 1960s. The United States Army commissioned the Ryan VZ-11RY in 1961, later redesignated as the XV-5A in 1962. This initiative was part of the Army's exploration of VTOL capabilities, alongside the Lockheed VZ-10 Hummingbird, which was later redesignated as the XV-4 in 1962. The XV-5 was equipped with two General Electric J85 GE5 turbojets, each providing 2,658 pounds of thrust. Vertical takeoff and landing VTOL capabilities were achieved through the use of General Electric X3535 lift fans integrated into the wings and a smaller fan in the nose. These lift fans were powered by engine exhaust gas. Each wing featured a 62.5-inch diameter lift fan with a hinged cover on the upper wing surface, which could be opened for VTOL operations. The 36-inch nose fan played a role in pitch control but posed challenges in terms of handling characteristics. The lift fans collectively generated vertical lift of approximately 16,000 pounds, which was nearly 3 times the thrust produced by the turbojets. Yaw control was facilitated by a set of louvered vanes beneath each wing fan, enabling the vectoring of thrust fore and aft. The XV-5 Vertifan was a part of the Army's exploration of innovative VTOL technologies during the 1960s, showcasing unique lift fan configurations for vertical takeoff and landing. The engine power setting determined the lift from the fans, as fan RPM was determined by the exhaust output from the J85 engines and the load on the fan. Roll control was by differential actuation of the wing fan exit louvers. Aircraft performance was subsonic, with delta wings superficially similar to those on the Douglas A4 Skyhawk. The Vertifan had an unusual intake position above the 2-seat side-by-side seating cockpit and a T-tail. The XV-5A was painted in army green, while the XV-5B had a white NASA color scheme. Despite its unique design, the lift fans on the XV-5 didn't generate the anticipated thrust, and the transition between vertical and horizontal flight proved to be challenging and abrupt. This aircraft marked one of the last crewed endeavors by Ryan, a company that shifted its focus to drone manufacturing in the mid-1960s. The XV-5 was part of a diverse array of attempts to create successful vertical takeoff aircraft. However, the lift fan system used in the XV-5 was heavy and occupied a considerable internal volume. Only the Hawker Siddeley Harrier remained operational by the turn of the 21st century, along with technology enabling the use of a shaft-driven fan in the Lockheed Martin F-35B. The combination of the J85 engine and lift fan in the XV-5 was a precursor to developments that led to the first high bypass ratio engine by General Electric, the TF-39. The lift fans were driven by turbine blades mounted around the fan's periphery, with a mass flow 13 times greater than that of the gas generator, and resulting in a 3-fold increase in thrust compared to a propelling nozzle. Following the demonstration that large volumes of air could be moved through a lift fan, an 80-inch tip drive fan, turned through 90 degrees and powered by a more potent J79 engine, was constructed to showcase an efficient cruise fan. This concept of a large diameter cruise fan was incorporated into the General Electric TF-39 engine utilized on the Lockheed CF-5 Galaxy. The XV-5, while not achieving widespread success, played a role in advancing lift fan technology and contributing to subsequent developments in aircraft propulsion. Two 12,500-pound XV-5As were evaluated in late 1966 by 15 test pilots. One was destroyed in a crash during a public flight demonstration on the 27th of April 1965, killing Ryan test pilot Lou Everett. As a result of this accident, the conversion switch was changed to a lift-lock toggle and relocated on the main instrument panel ahead of the collective lever control. The XV-5 presented challenges during landing due to various factors. Yaw control relied on altering the angle of the lift fans in opposing directions, but this method proved insufficient for precise low-speed handling. The duct doors further complicated control, causing significant pitch changes even at low speeds. Additionally, the aircraft experienced poor acceleration during standard runway takeoffs. Promotional materials and tests explored the potential of a rescue version equipped with a winch to hoist individuals into a compartment behind the pilots. However, a tragic incident occurred on October 5, 1966, during trials for the rescue aircraft. The second XV-5 sustained extensive damage when a suspended horse collar survivor sling was drawn into a wing fan. Despite the fan still functioning well enough for controlled flight, Major David H. Tittle, the pilot, suffered fatal injuries due to the ejection seat propelling him out of the aircraft after it hit the concrete airport surface. Following the accident, the second aircraft was reconstructed as the modified XV-5B, and testing continued until 1971. An XV-5B is currently on display at the United States Army Aviation Museum in Fort Novosel, Alabama. Despite the cancellation of the program, the ducted fan concept was deemed successful, leading to several proposed follow-up programs. The ducted fans were recognized for their quiet operation, especially for the era, and their ability to operate from standard surface materials without causing damage. This set them apart from other VTOL aircraft, which often require protective mats to prevent ground surface damage from their exhaust, a concern mitigated by the cooler exhaust from ducted fans. In 2004, renowned director Martin Scorsese released the feature film The Aviator, which garnered 5 Oscars. This cinematic masterpiece sparked widespread interest in one of America's most extraordinary figures, billionaire Howard Hughes. Among his many ventures, Hughes undertook the ambitious project of creating a colossal amphibious aircraft known as the Hughes H-4 Hercules. This flying boat, constructed as a singular prototype, made its historic maiden flight on November 2, 1947. Despite only completing a single flight, Hughes's Hercules secured its place in history as the largest flying boat ever built. Its monumental wingspan of 98 meters remains unrivaled to this day, surpassing even the dimensions of aircraft such as the AN-124 Ruslan and the AN-225 Emria. During the early stages of World War II, Allied forces initially underestimated the threat posed by Nazi Germany's submarines. Lessons from World War I had been disregarded, leading to catastrophic losses in naval trade. While losses from German submarine attacks were initially manageable during 1939 to 1940, the situation escalated dramatically in 1941 to 1942. The German Kriegsmarine unleashed a reign of terror across the vast expanses of the Atlantic, sinking nearly 700 Allied ships in the first 7 months of 1942 alone. It wasn't until the latter part of 1942 that the situation in the Atlantic began to improve, primarily due to a significant increase in the number of escort ships deployed to protect convoys. This concerted effort helped mitigate the threat posed by German submarines, albeit after considerable losses had already been incurred. Despite these actions, the threat from German submarines was not eliminated. In such conditions, the idea was born that would protect valuable military goods from Kriegsmarine attacks. Cargo could be shipped across the Atlantic Ocean not only by water, but also by air. However, the implementation of this idea would only be possible with the creation of a transport plane of sufficient carrying capacity. To address the pressing need for a solution, shipbuilder Henry Kaiser proposed the design of a large transport flying boat. Renowned billionaire and aircraft designer Howard Hughes enthusiastically took on the challenge of bringing this concept to fruition, resulting in the creation of a giant aircraft that remains unparalleled to this day. In 1942, the US government contracted Howard Hughes to construct a single prototype aircraft, driven by the vision of a sizable flying vehicle to support naval operations. The result was a multi-ton wooden amphibious aircraft with a remarkable wingspan of almost 100 meters. Initially designated as the NK-1 Hercules, this flying boat boasted impressive dimensions that continue to impress. a fuselage spacious enough to accommodate over 700 soldiers, weaponry, and approximately 60 tons of commercial cargo. To provide the necessary power for this colossal aircraft, 8 engines were installed in its wings. The project's development was guided by a specific goal: to construct an aircraft for cargo and passenger transportation while minimizing the use of strategic raw materials. Consequently, the decision was made to build the aircraft from wood rather than aluminum. The envisioned role for this flying boat was to transport troops and various cargoes from the United States to war-torn Europe along a secure air route, circumventing the threat posed by the German submarine fleet. Working documentation for the new flying boat was developed very quickly, which cannot be said about the pace of the aircraft construction itself. The works that began in 1943 were fully completed only by the middle of 1947. This slowdown in the construction of the aircraft was influenced by several reasons, ranging from the end of the Second World War, as a result the military lost interest in this car, and ending with various legal proceedings against Howard Hughes. Disputes regarding the funding for the project persisted throughout its execution, reflecting differing opinions on its necessity. One dissatisfied US senator famously referred to the future amphibious aircraft as a flying forest warehouse, but it garnered another well-known nickname, the Spruce Goose. A substantial sum from the US state budget, totaling $22 million, a considerable amount for the time, was allocated for the project's implementation. However, this funding proved insufficient, prompting Howard Hughes to personally invest an additional $18 million into the endeavour. The flying boat, subsequently renamed the N-4 after Henry Kaiser's departure from the project, marked the 4th aircraft of Howard Hughes's own construction. On November 2, 1947, the N-4 made its inaugural and final flight, piloted by Hughes himself. The aircraft undertook a brief flight, ascending to an altitude of 21 meters and traversing a 2-kilometer stretch along the coast of Los Angeles. With this flight, the saga of the Hercules nearly came to a close, transitioning abruptly from the realm of active aviation to that of a museum exhibit. Ultimately, this costly and sizable flying boat proved to be of little practical use at the time. The Hughes H-4 Hercules was characterized by a hull, a cantilever wing, and 8 radial engines. The flying boat had a vertical and tail plumage, as well as fixed wing floats. The entire structure of the aircraft consisted of laminated wood, but contrary to the nickname in the construction of the flying boat, it wasn't spruce, it was birch. At the Howard Hughes plant, woodworking was able to achieve high aviation standards. The construction of the aircraft involved creating full-size patterns of structural elements, from which matrices were produced for moulding the parts. The thinnest piece, with a thickness of 1.2 mm, consisted of 3 layers, each 0.4 mm thick. Conversely, the thickest part measured 254 mm in thickness and comprised 200 layers of veneer, each 1.27 mm thick. To maintain the integrity of the veneer layers during gluing, double-capped nails were utilized. Once the glue had set, these nails were removed using a special nail puller, resulting in the extraction of approximately 8,000 nails across the entire flying boat. The resulting holes were then sealed with a specialized putty. Following assembly, a thin layer of primer was applied to the surface, succeeded by a layer of rice paper and 2 coats of protective lacquer. The exterior surfaces of the aircraft were coated with aluminum paint, concealing the fact that the aircraft's underlying structure was composed of ordinary wood. Both the aircraft's skin and its structural components appeared as if they were made of aluminum. The cargo compartment of the amphibious aircraft featured 2 levels, interconnected by a spiral staircase. Hinged doors located at the nose of the aircraft facilitated the easy passage of 2 railway cars or a Sherman M4 tank. This design ensured the versatility and practicality of the aircraft for transporting various types of cargo. At that time, the Hughes H-4 Hercules was the only aircraft that was able to transport the tank through the air. In the best traditions of submarines and ships, 18 seal compartments were provided in the design of the seaplane. 6 of them were enough to keep it afloat. The electrical equipment of the aircraft operated from direct current with voltage 120B, since with traditional 24B, the cross-section of the wires, the length of which reached 50 kilometers, was very large. The seaplane was to be lifted into the air by 8 huge radial air-cooled R4360 Wasp major piston engines from Pratt & Whitney. Each of these engines developed 3,000 horsepower. The engines of the aircraft were equipped with 5-meter 4-blade propellers. Of the 4 engines positioned closest to the fuselage, 4 were capable of generating reverse thrust, granting the giant aircraft the remarkable ability to maneuver independently in reverse and execute tight turns. The expansive size of the flying boat facilitated in-flight engine repairs, as special passages within the enormous wing allowed access to the engines. At the point of attachment to the fuselage, the wing section reached a height of 4 meters. Despite its unprecedented scale, only a crew of 3 individuals was required to operate the aircraft. The collaborative effort between Hughes and Kaiser aimed to produce the largest aircraft ever constructed, surpassing any previous aircraft in size by a staggering 7-fold. This ambitious project stands as one of the most remarkable endeavors in aviation history. The determination and valor of Howard Hughes and his dedicated team, who persevered despite numerous challenges, culminated in the historic flight of the H-4 Hercules. However, tensions arose within the project leadership, leading to significant contradictions. Henry Kaiser advocated for the construction of a 70-ton aircraft to adhere to deadlines and present a finished product to the military. Conversely, Howard Hughes insisted on building a 200-ton airplane, necessitating greater investment of time and resources. This discord ultimately led to Kaiser's departure from the project, while Hughes became increasingly enamored with the idea, incorporating new improvements and proposals that further prolonged the construction timeline of the flying boat. As a result, in 1942, this order was urgent for the US government, but by 1944 it lost its relevance. By this time, the situation on the fronts of World War II had changed radically, and the interest of the United States in the project gradually faded away. The US government had contemplated cancelling the contract for the seaplane's construction, but by then, Hughes's motivation had transcended mere practicality. He had become consumed by the idea of creating a cargo aircraft that would surpass even the most extravagant imaginations of his contemporaries. On November 2, 1947, the Hercules was launched, and Hughes, alongside his small crew, initiated the aircraft engines for the first time. Following several water taxi tests in front of a sizable audience, predominantly journalists, the flying boat lifted off from the surface of the Los Angeles harbor without any prior announcement, embarking on its inaugural and final flight. Maintaining an altitude not exceeding 20 meters, the Spruce Goose traversed approximately 2 kilometers at a speed of 120 kilometers an hour before executing a flawless landing. This unauthorized test flight, undertaken in defiance of an official ban on taking the plane airborne, served to silence numerous critics of the project, demonstrating that the largest aircraft in history was indeed capable of flight. Many regard this flight as one of the most significant moments in the annals of aviation history. Following its historic flight, the Spruce Goose returned indefinitely to its hangar, a colossal structure specially constructed to house it and prevent it from ever taking flight again. At Howard Hughes's behest, until his passing in 1976, the flying boat remained in a state of perpetual readiness, with its engines started every month. Initially, a team of 300 individuals monitored the aircraft's condition until the 1950s, when the staff was reduced to 50 people. Nevertheless, the annual cost of maintaining the Air Giant in flight-ready condition amounted to approximately $1 million. Additionally, the construction of the hangar where the Hughes H-4 Hercules was preserved for eternity incurred costs of around $2 million. Currently, this unusual aircraft is an exhibit at the Aviation Museum in McMinnville, Oregon, where it was transported in 1993. At the same time, over the past 50 years, this flying boat has become one of the most beloved artifacts of the United States, moving from a state of almost total uselessness to the category of object of cultural heritage. Today, the story of the Hughes H-4 Hercules, which soared into the sky only once in its lifetime, is revered as a testament to its creator's unparalleled resolve to see the project through to completion, transforming the aircraft into an emblem of the 20th century. Regarded as a symbol of determination and ingenuity, the Spruce Goose continues to captivate the imaginations of people worldwide. Drawing over 300,000 visitors annually, the aircraft stands as a living testament to Howard Hughes's extraordinary vision and perseverance. Its towering presence serves as a reminder of the boundless ambition and unwavering commitment that characterized an era of pioneering aviation endeavors. Through its enduring legacy, the Hughes H-4 Hercules remains an enduring symbol of human achievement and innovation. Built for the Air Force by Martin, the X-24A was a bulbous-shaped aircraft with 3 vertical fins at the rear for directional control. The X-24A boasted a weight of 6,270 pounds without propellants, with dimensions measuring just over 24 feet in length and nearly 14 feet in width. On April 17, 1969, Air Force Major Gerald Gentry piloted the X-24A for its inaugural unpowered glide flight. Gentry also commanded the vehicle during its first powered flight on March 19, 1970. Over the course of its operational lifespan, the X-24A undertook 28 flights, contributing to the validation of the concept that a wingless vehicle could execute unpowered landings akin to the HL-10 program. Decades later, in a cost-saving measure, the X-38 program managers opted to utilize the X-24A design, leveraging its complete aerodynamic database to minimize the need for additional wind tunnel tests that would have been necessary for a completely new design. The X-24A recorded its fastest speed of 1,036 miles per hour, Mach 1.6, with its highest altitude reaching 71,400 feet. Both of these milestones were achieved by NASA research pilot John Mach, who also piloted the craft on its final flight on June 4, 1971. The X-24B's design evolved from a family of potential re-entry shapes proposed by the Air Force Flight Dynamics Laboratory, each with higher lift-to-drag ratios. To reduce the construction costs of a research vehicle, the Air Force opted to return the X-24A to Martin for modifications. These alterations transformed its bulbous shape into a configuration resembling a flying flatiron, featuring a rounded top, flat bottom, and a double delta planform culminating in a pointed nose. John Mach took the helm for the maiden flight of the modified X-24B, piloting its first glide flight on August 1, 1973. He also commanded the vehicle during its inaugural powered mission on November 15, 1973. Notably, among the X-24B's final flights were 2 meticulously executed landings on the main concrete runway at Edwards, showcasing the operational feasibility of precise unpowered re-entry vehicle landings. These pivotal missions, executed by Mach and Air Force Major Mike Love, played a crucial role in shaping the flight procedures for modern space shuttle landings. The X-24B's last powered flight was on September 23, 1975, with Bill Danner at the controls, marking the conclusion of rocket-powered lifting body flights at the Flight Research Center. Interestingly, Danner also piloted the final X-15 rocket plane mission approximately 7 years prior. The X-24B achieved a top speed of 1,164 miles per hour, Mach 1.75, during a flight piloted by Love on October 25, 1974. Its highest altitude reached was 74,100 feet, accomplished by Mach on May 22, 1975. Today, the X-24B stands proudly on public display at the Air Force Museum located at Wright-Patterson Air Force Base in Ohio, serving as a tangible testament to its significant contributions to aerospace research and development.
From 1933 until the end of the Second World War, German aviation led the world in aerodynamic design and technical innovation. Long before the outbreak of hostilities, German industry produced an armada of technically superior warplanes. When war broke out, the Luftwaffe quickly overwhelmed some of Europe's most vaunted air forces. Classic designs like the Bf-109 fighter and Ju-88 proved to be superior fighting machines, while others like the Blohm+Voss BV-141 became one of aviation's true oddities. The Blohm+Voss company was one of the first to respond with their BV-141. Designed around the concept of maximum all-round view, the BV-141 was in many ways a problem looking for a solution. The unorthodox design featured an asymmetric layout with the radial engine installed at the front end of a portside tail boom and an extensively glazed crew nacelle mounted to starboard. Unusual and radical in design, the BV-141 performed surprisingly well, but in the end it was considered too unconventional and it was cancelled in 1943.
Yes, in my meandering throughout Germany, just after the capitulation, I was looking for unusual or advanced technology aircraft. And the 141 intrigued me a little, but I had heard that they were at an airfield called Grossenhain, which was quite near Meissen. There was a big reconnaissance unit which had many reconnaissance types of aircraft, and I thought maybe the 141 will appear there. So I flew there, and there was no sign of one, but I asked if I could speak to some of the POWs who were in the cage there, and one of the chaps told me that a 141 had indeed been there, but the last he remembered of it was not too long ago. It had had an engine problem while flying nearby and had landed on an emergency strip east of Grossenhain. So I flew over in that direction looking for this strip. But it wasn't really a strip, I found. It was a small airfield. And it was, by this time I'd moved into the Russian occupation zone. And I decided to land there because I had already found that at that stage after the war, the Russians were still very amenable to the Brits because we had come in at the early stages of the war to help them. Anyway, when I landed, there weren't a lot of aircraft there, and there was a Russian commissar and with an interpreter, and I asked if there was a 141 there. He didn't really know things like the aircraft numbers, but he said there were one or two aircraft left, but his people had examined the airfield, taken away what they wanted, and the rest was left for destruction. So I said, could I have a look around, see what it was? He said, well, yes, why not? Because it's all going to be destroyed anyway. And in one hangar, there was indeed a 141. It had regularly had its engines run up by Feldwebel, who was available. And I said to him, was the aircraft flyable? And he declared, oh, yes, it was. I rather suspected his motive, so I wasn't too sure of what he was saying or believing what he was saying, because I think he had hoped I would fly him out of there and out of the Russian zone. But the Russians were obviously not going to play with that. Anyway, I thought I'll take his word for it and have a go at this. And the commissar didn't object. He said, as long as I stayed within sight of the airfield, and I'd only have enough fuel to do that, he didn't mind, because it was due for destruction anyway. And so he let me fly that, and I had about 30 to 40 minutes in it to try out this theory that it flew very nicely in a straight line when on an angle, a bank of 90 degrees. And after about 2 or 3 goes at this at various speeds and heights, I had trouble with the engine, so I had to return to base. And so I formed an impression that it probably did what it said it could do, but its real reason for failing, in my opinion, was it certainly wasn't an aircraft in the same category of handling as the Focke-Wulf 189, which I had already flown, and was its competitor.
Another odd-looking aircraft was the Focke-Wulf 189. The completely glazed central nacelle, twin engines and tail booms were considered too radical for conservative Luftwaffe officials. Performance, however, won the day. Known as the Flying Eye, the FW-189 proved supremely versatile, universally popular, and one of the most reliable aircraft ever to see Luftwaffe service. During combat operations, the FW-189 surpassed all expectations. Despite flying low over the battlefield and taking large amounts of damage, it had the ability to absorb punishment and fight another day.
So I think that killed it more than the theory that it gave the gunner a wonderful field of fire by having no starboard half of the tailplane and being asymmetrically offset to give a clear field of fire to the gunner. So that was my experience of it. Not very impressive, but interesting.
In the early part of 1953, a new concept in military aircraft was about to take shape, a concept which evolved from the joint effort of Air Force planners and Lockheed designers, shaped by Air Force experience in recent conflicts. The concept of the lightweight fighter, supersonic, low in cost, easily producible, XF-104. Work began in March. Plans had to be drawn up, a mock-up completed, tooling prepared, and plant space cleared so that production crews could start work on the first of two prototypes. A challenging schedule was set up. The first prototype was to be completed and into flight test by March of 1954, less than a year away. Work went ahead swiftly. Experimental jigs were designed and put together in the shop area. In adjacent areas, machined parts were made, parts which had to be milled and bored and cut, shaped for use in early fabrication stages. Actual fabrication was soon underway, and through the production processes of sub-assembly and assembly, the F-104 began to take shape. In the meantime, wind tunnel tests were conducted in the company's subsonic tunnel. A range of low-altitude, low-speed conditions were generated to simulate the force and load factors which would act on the F-104 during takeoff and landing. Measurement of these forces and loads, in turn, would furnish information to the design of landing gear, flaps, and controls. Wind tunnel work at this time also included a series of flutter tests conducted through a wide range of airspeed-altitude combinations. A direct control device was used to bend the wings to a calculated degree. Motion pictures furnished a visual record of results, while direct readings of flutter amplitudes and frequencies were made by oscilloscope. Sudden release of the wing induced flutter. Engineers used the wind tunnel to further advantage in a series of tip tank tests. High-speed photography showed that separation of the tank from the wing was immediate and clean. By mid-October, the main fuselage was well underway, and work went ahead on the empennage, wing, and stabilizer. In the meanwhile, Lockheed engineers had gone to the Ames laboratory at Moffett Field, where the superb technique and equipment of this NACA facility were used to prove out design of the 104 and to gather data on its aerodynamic behavior in both subsonic and supersonic ranges. Tests aimed at determining the span-wise distribution of various force and bending moments. Leading and trailing edge structures were investigated, as well as the effects of tail buffeting. The final series of wind tunnel tests was carried out at the NACA facility at Langley Field, adding a full range of transonic data to the subsonic and supersonic data already collected. Free flight tests provided further and highly realistic confirmation of design ideas. 5-inch high-var rockets were used to impel a scale replica of the F-104 straight-thin wing through the air at supersonic speeds. A gunsight camera mounted on the rocket photographed wing behavior during flight, making available a record for later study. A replica of the 104 tail section was tested in the same way. Towards the close of 1953, construction was well along on the forward section of the fuselage. It was taken from its jig on December 1st and moved to the assembly area for mating with the aft fuselage section. Immediately before mating, each section was weighed to determine that actual weight did not exceed planned weight. In the meantime, the wings had been finished so that they could be joined to the fuselage as soon as it was ready. While the manhandling method shown here would not be used in production phases, it does serve to show the simple design and lightweight qualities inherent in the 104. With the fuselage almost ready for outfitting, attention was given to the items which would be installed in it. An exhaustive series of tests, for example, was going forward at the drop tower, where the 104 landing gear was mounted on the testing apparatus and subjected to shocks and loads far in excess of any it would experience in actual use. After drop tower tests had proved structural strength, the gear was installed in the 104 prototype. A series of run-throughs checked clearances, hydraulic activation, and other operational features. Further valuable time was gained on 104 development by handling several projects concurrently. Armament is an example of this kind of parallel growth. Specialists devised and tested in mock-up a storage box to hold 750 rounds of 20mm ammunition and provide a direct free-flow feed to the T-171E2 gun. With revolving barrels and a very high adjustable rate of fire, the T-171E2 has been chosen as the most satisfactory weapon for the prime mission of the XF-104, that of day or night, air-to-air fighter. The choice is by no means rigid, however. The 104 promises considerable versatility, and provisions have already been made for the installation of a rocket platform in the present gun bay. The platform will be extended for firing and retracted after use. Meanwhile, the first 2 months of 1954 saw the first 104 prototype drawing close to completion. With the mating of the aft fuselage section to the main section, major assembly was complete, and the way stood open for the running of vibration tests. These tests determined the natural frequency patterns for the entire 104 structure. When the vibration test program was complete, the 104 was ready to enter flight test. The F-104 left the plant in the early morning of February 25th. Strict security prevailed, and by daylight the prototype arrived at Edwards Air Force Base, 347 days from the go-ahead date. Flight crews began at once a schedule of pre-flight work, submitting systems and operating parts to a thorough round of checks and rechecks. The engine selected for early flight testing was the Wright J-65W1. thrust of the J-65 is sufficient to guarantee supersonic performance for the 104. The airplane can accommodate any of several alternate power plants, and with such an engine as the General Electric J-79, for example, speed and performance would be superlative. Engine run-up was a necessary prelude to flight test, now only a few days off. A major flight safety feature of the 104 is that seat ejection is downward. Getaway is clean and immediate, with no possibility of canopy interference or of the seat striking portions of the craft during ejection. Downward ejection also enhanced the simplicity of cockpit layout and canopy and controls design. In the matter of flight station arrangement, Lockheed engineers spent many hours in consultation with Air Force pilots. The pilots made clear their recommendations for a practical, efficient cockpit, and the F-104 follows their indications. Controls are logically grouped and easily operated. In the 104, primary controls are the conventional stick and pedal type. The final pre-flight procedure consisted of a controls check. A cable system operates the rudder. Stabilizer and ailerons are controlled by hydraulically operated, irreversible systems. Secondary flight controls include leading edge flaps, landing flaps, and dive flaps, all power operated. Just before the date of the first flight, a series of taxi runs was made. On February 28th, one day ahead of schedule, the craft became airborne. On the morning of March 5th, 1954, 355 days from contract signature, the 104 was ready for its second flight. This flyover offers a good comparison of the size and plan form of the 104 with other military types. The thin, straight wing, with its 10 degrees negative dihedral, conferred excellent lateral stability and side-slip characteristics on the craft. Control response was quick and sure. The airplane came through. It handled firmly, surely.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.